All right, this set of notes includes sound waves and builds upon the intro to wave characteristics that was just completed. All right, as you've been learning through the Arduino projects, as you've been making sounds of different frequencies, frequency is equivalent to pitch, right? So if you have a wave that is vibrating frequently, many vibrations per second, that would be a higher squeal pitch, as opposed to a lower frequency pitch where there are less vibrations per second. Right? Our human ear is capable of detecting frequencies in a certain range. Lower end about 20 hertz, upper end about 20,000 hertz. However, this range drops with age. I saw a pretty good stat that at 16,000 hertz, 90% of people over the age of 30 are not able to detect it. However, people under the age of 30, there's about 90% that can. All right. So as time goes on and loud sound wave into your ear damages internal parts. Right. Different beings, right? This like list of animals are able to hear higher frequencies than humans can. Notice bats all the way up to about 120,000 hertz. All right. So not are all created equal. If we ever have sound waves that are above the frequencies in which we can hear, we refer to them as ultrasound or ultrasonic. If they're less than what we can hear, we refer to them as infrasonic. You've probably heard of these prefixes before. Ultra means greater. So when we talk about light, ultraviolet is above the frequency of violet light. Infrared is below the frequency of red light, right? Infrared's like used in your remote controls to control TV. Okay? Now, a sound wave is what's referred to as a longitudinal wave, right? That is when the energy of a wave moves parallel to the shaking of the molecules. So here, when we strike this tuning fork, you can envision the energy of the wave moving across the screen here, and the actual molecules shake back and forth in that same direction, kind of like punching a slinky, right? Rather than shaking it up and down. The places where the air molecules are all bunched up are called compressions. Rarefactions are where they're spread out, and this actually leads to a pressure difference through the air. Right? Those tuning forks I've shown in class, they're really hard to see them shaking back and forth because it's many vibrations per second. All right, but the key thing of vibration is one full back and forth. The shorter the legs of the tuning fork tends to be a higher pitch or higher frequency. Longer legs, right? It takes more time to shake back and forth, hence lower frequency. Right? Now, the speed of sound waves depends on several factors. Number one thing, though, is temperature. So at room temp and what's called standard pressure, sound waves travel at about 343 meters per second. This is in the ballpark of around 750 miles per hour. On the other hand, if you have electromagnetic waves, right, light waves, as talked about in the previous set of notes, they move at the speed of light, which is well above the speed of sound. So there's a big difference. That's why thunder and lightning are detected at different times, right, when they travel over distances because they change the difference in that speed. Okay. Also depends if you're moving through a liquid or a solid, right? A sound wave is a mechanical wave. It needs a media to move through, right? So this is just kind of a nice list here. If you compare air at freezing versus room temp, you see there is a significant change in the speed of sound, 332 up to 343 meters per second. Sound travels through water much quicker and then much more quickly in different solids. right? And depend upon their molecules and how closely packed they are, changes what that speed is within them. Right? If you ever heard of an echo, all an echo is a reflection of a sound wave off of a nice smooth surface and back. So if you're doing any problems in your problem set, remember that an echo is a full round trip, to hit the object and come backwards. Right? A lot of animals, this is how they see, right? They send a sound wave out, and when it comes back to them, they know that something is in front of them. And that's how your ultrasonic motion sensor in your Arduino kit works. If you've ever seen like fish finders, sonar, it's that same principle, an echo or a reflection of a sound wave. Okay, now, energy in sound waves, there's not tremendously high, but remember, they carry energy, not necessarily the particles. So when I speak, right, the air molecules here do not go across the room into your ear, right? It's actually the energy that gets to your ear, and that's how you detect sound. Okay. So as said before, they're really small energy levels. All right. But how we measure kind of the loudness or energy in a sound wave is what's called a decibel level. All right. And the baseline of 0 decibels is like at the bottom of what we can hear, right? It's like kind of that 0 point. The key thing with the decibel level scale is it's logarithmic. It's not linear. So what happens is that the amplitude of a sound wave goes up by factors of 10 for every 20 decibel increase. Okay. It's kind of like the Richter scale. The Richter scale goes up by a factor of 10 in energy output for every one you go up on the Richter scale, right? It's not linear, meaning an earthquake of a magnitude 8 does not have double the energy as a 4, right? It's much, much more than that. So that's what's referred to as a log scale. Right? I'm going to show an example at the end of the video. This is just a nice little picture on what we can hear depends upon both the frequency as well as the decibel level of that sound wave. So kind of in the middle is where we speak here. The outer ring is kind of what we can detect. So it depends on both those things on how loud something might sound to your ear. That's why a lot of kind of the headphones to protect your ears. If you're out doing yard work, they actually have a noise reduction rating on them. Talks about how many decibels it drops it by having that protection on. Right? So as the example for decibels, I just wanted to show this real quick before ending this. It's all about comparison. So say we had a 32 decibel level sound wave, and then we cranked it up to 52 decibels. To compare those two, that would have 10 times the amount of amplitude. Right? If we did a 32 decibel sound wave as a baseline and cranked it up to 72 decibels, because that's an increase in 40 decibels, which is 2 sets of 20, that would actually be 100 times greater in amplitude. Because it's logarithmic, if we went into in-between sections, say for instance we had a 42 decibel sound compared to 32, that's halfway. That would actually be an increase of 10 raised to the 1/2 power, which is the square root of 10, which is a little bit more than 3, right? If we actually had a 62 decibel sound wave compared to 32, that would be 10 to the 1.5 power, which would be 10 times the square root of 10, which would be a little bit more than 30. And you've been doing some exponent stuff in Algebra 2 lately, so hopefully you see that kind of connection there. Okay. Good luck on the pitch and sound, pitch and loudness practice sheet in your Google form.